Okie dokie nerds, as promised, graphing, and we have come back to the stuff that I skipped in order to do section 9.6 yesterday. We're going to do sections 9.3 and 9.4 together because I felt like it was a waste of our time to do section 9.3 separate from 9.4. The homework assignment would have been like 2 questions if I had done that. It really wasn't worth separating the two. So that's why I put the two together. We're not going to finish this lesson in one day. That means you don't have to have the homework done by tomorrow, but you should try to do the first 4 questions from the homework. And you'll notice there's only 7 questions on the homework. You should try to do the first 4 tonight. At least the first 3, but you should do the first 4. Graphing rational functions is what we're talking about. A rational function, just to remind you, is anything that has an x in the denominator. We call this a rational function. The most important thing about any function, as far as I'm concerned, is the domain. What values are you allowed to use in your function? So this first one says find the domain of the function. Look, we have been practicing finding the domain since chapter 1. This is a fraction. What's the only rule about fractions? The denominator can't be 0. You are not allowed to divide by 0. There is a single number for x that would make us divide by 0. What is that x value? Everyone, please. 2. Yeah, thank you, half the people, even though I said everyone. What that tells us is that x simply can't be 2. So that's not the domain. That's the domain restriction. What is the domain? It's everything except for 2. So our domain would be all the numbers to the left of 2, which means all the way out to negative infinity, up to the number x equals 2. You can't include it though, so it gets a parenthesis and not a bracket. We can also use, union symbol, everything beginning at 2 but not including it and going to the right, out to positive infinity. So there is your domain, everything except for 2. That's how you would write that domain. Everybody cool with that one? It's pretty easy, right? All right. Alrighty, so then what does the parent rational function look like? Boom. There it is. It's actually called the reciprocal function because it's 1 over x. It's the reciprocal of y equals x. But this is the parent rational function. This kind of shape is called a hyperbola. I won't test you on that, but you might as well know that's what that kind of shape is called. It has a domain of everything except for what would have made you divide by 0. So you can't use x equals 0. This thing's domain then is negative infinity to 0, and then from 0 to infinity, which you could see in the image. The range is all the y values it can cover up. As it turns out, the only y value this will never equal is also 0, because 1 divided by every single number, except for 0, is going to be a non-zero value. There is no way to divide a number by something and get 0 as an answer. It just so happens. So its range is the same as its domain. Is that always the case? No, that's the case for the parent. It is continuous, meaning, well, as far as you know, meaning exists everywhere except for x equals 0. That's not the true definition of continuity. You won't get the true definition of continuous until you know some calculus. For now, your definition of continuous means smooth, unbroken curve. That's not its real definition, and there's exceptions to what I just said, but there you go. This is an always decreasing graph. Put your roller coaster car anywhere on the curve and let it go. And as it goes from left to right, it's going to fall. Ah! And if you put it over here and you let it go, it's going to fall. Ah! Okay? So this is an always decreasing function. It has odd symmetry. So reflecting it upside down over the x-axis, boonk, is the same as reflecting it left-right over the y-axis. Boonk. Either way, it puts the two curves in quadrants 2 and 4. So it's odd, oddly symmetric. Reflecting over x is the same as reflecting over y. It's unbounded because it goes forever up and down. It has no maximums, no minimums, and then asymptotes. Now, we've worked with asymptotes before this year. When we learned about exponential functions, we learned that all exponential functions have a horizontal asymptote, a y value that they approach, that they never reach, but they get infinitely close to. Okay, the definition of a horizontal asymptote, the true definition of a horizontal asymptote is simply a y value that you will get infinitely close to. It actually has nothing to do with whether or not you ever reach it, which I know seems kind of contradictory with what I said. But rational functions sometimes do this neat trick where they'll cross the horizontal asymptote, like they'll go past it, and then they'll come back towards it and get infinitely close to it towards all infinity. So the definition of any asymptote is a structure that you will get infinitely close to. That's the definition of an asymptote. A horizontal asymptote will be a y value that your graph gets really close to at the far left and the far right. A vertical asymptote is a vertical line that you will get infinitely close to as you go up and down. But it just so happens vertical asymptotes always occur, for rational functions at least, when you try to divide by 0. So a vertical asymptote will always be a place where the graph was not allowed to exist. So coincidentally, your graphs will never cross a vertical asymptote, because vertical asymptotes always occur at domain restrictions. Always. But the true definition of any kind of asymptote is a structure that your graph gets infinitely close to. For end behavior, as this thing goes to the far left and as this thing goes to the far right, I'm hoping you can see that on both of the infinities, it gets infinitely close to the line y equals 0, the x-axis. So there you have it. There's your graph getting infinitely close to a y value at either end. So if your graph approaches a number, a y number, either to the far left or to the far right or to both, that is a horizontal asymptote. I will, for space purposes, never write vertical asymptote, and for space purposes, never write horizontal asymptote. Instead, I'm going to write VA and HA, because that is just less crap. And if you look at your homework, I've used shorthand, VA and HA. I've also used shorthand for y-intercept and x-intercept. Okay? And lastly, in this informational box is standard form. We like standard form because standard form will show us all of our transformations that have occurred. This is your up and down transformations, shifting. This is your left and right shifting. And A is going to show you both your reflections, if it's negative, and your vertical dilations, stretching and shrinking. Mr. M, I don't see a number in front of X. Does that mean we can never horizontally stretch or shrink? No, that's not what that means. What that means is if there is a number in front of X, there's technically a way to manipulate the equation so that the number comes out of the bottom and works its way to the top. So every horizontal stretch or shrink can actually be written as a vertical stretch or shrink if you do it correctly. What does that mean for you? That means I will not put a number in front of X and then ask you to describe that as a horizontal stretch or shrink for rational functions. That's what that means. Okay? I will not do that. And I won't put it there and make you represent it as a vertical stretch or shrink. Now, could that end up being an extra credit question? Sure, it could. Because it's outside the scope of what I have to teach you, but you should still be able to pull it off and understand what it means. So, you know. Boop. Let's say for this one. You see there's a number in front of X. That's why the directions don't say to describe the transformations. Because I wouldn't want you to describe this as a vertical stretch of factor 2 and then a horizontal shrink of factor 1/2. That seems like a pain in the butt. You can write what I'm doing, but I'm never going to make you do this. I'm just demonstrating how it could have been done. You could factor this 4 off the bottom as a GCF if you wanted to, and you could have done this. And instead of saying there's a 2 here and a 4 there, you could say that there's a 2 here and a 1/4 here. So you could be represented like this. So technically, that's standard form. That sucks though, doesn't it? Isn't that awful? This is really, really bad. So if you were going to describe the transformations from standard form, you wouldn't do it from here, you'd do it from here. So you'd be like, oh, vertical shrink, factor 1/2, shift left, shift right, 5/4 units, shift down 1 unit. And that's why I'm not going to ask you, I won't put a number in front of X and ask you to do that. I just wanted to show you how it's done. Instead, what we're going to do is we're going to try to graph this thing. And we're going to pretend that we have no idea what these things would look like. And when you have no idea what a function looks like, what do? You throw x's at it and you see what y's you get and you just connect the dots. That's how you do it. That's how you've always done it. Before I do that though, what I'd like to do is identify my 2 asymptotes. My vertical asymptote is always going to happen when you try to divide by 0 for rational functions. And that's not allowed. So you go, all right, 4x minus 5 equals 0. And we have to solve for x. Add 5. And then divide by 4. And since we're going to have to graph this thing, I'll turn it into a decimal. There. So if this is 1.5, this is 1.25. Cool beans. You know what? Look at that. That 5/4 showed up. Here's why. Your vertical asymptote is supposed to be at x equals 0. This has shifted to the right 5/4 units. Oh, look where it landed. X equals 5/4. See? Your horizontal asymptote is supposed to be at y equals 0. Bless you. It's supposed to be at y equals 0. What did this do to the graph? Moved it down 1. That means everything about the graph moves down 1, including the horizontal asymptote. So this right here will always be used to find the horizontal asymptote, and this right here will always be used to find the vertical asymptote. Okay, got you. So this is my horizontal asymptote, y equals -1. And you do have to say x equals for the vertical asymptote. You do have to say y equals for the horizontal asymptote, otherwise it's wrong. But y equals -1 is here. There we go. Now we're going to fill out our table, and we'll do our best to plot those dots. Is everything okay so far? If not, say something to me. I want to help. Everybody's good? Cool. All right. Scientific calculator time. Going to plug in -2. So 2 divided by. Remember, you need to use parentheses when you have lots of stuff in the bottom of your fraction. So I say parentheses, 4 times -2. Don't use the minus sign. Make sure you use the negative key that's down here. -2. And then I've got -5. Close the denominator. And then -1 equals. And it gives you your number of -1.15-ish. And you might be thinking like, man, that was a lot of stuff to type. And I have to do that how many times? Well, here's the good news. If you're using this scientific calculator, you don't have to retype it. Because you could just hit the up arrow, and then you can go change the x that you typed in. We've done that before this year. I'm going to type a 1, now it says -1. hit enter again. Negative 1.22. I can hit the up arrow again. There's no such thing as negative 0, so I'm going to delete the negative symbol, and now I'm just going to type the 0 and hit enter. Negative 1.4. Up, replace the 0 with a 1. Negative 3. It would appear as though, as I get closer to the value of x equals 1.25, my values are going down and down and down, which shouldn't be surprising because we have an always decreasing function. We're currently approaching our vertical asymptote, which is forcing us to shoot straight down. Now 2 is to the right of my vertical asymptote, so I should now have a y value that is bigger than what I've been getting. Let's see. Negative 1/3. Negative 0.3 repeating. Go up, change it to a 3. Negative 0.71. Make it a 4, make it a 5. It would appear as though as I go further to the right, I'm getting closer and closer and closer to negative 1, which should make perfect sense because I'm approaching my horizontal asymptote. Now we're just going to try to plot those points. Negative 2, comma, negative 1 and change. Negative 1, comma, negative almost 1 1/4. 0, comma, almost negative 1 1/2. 1, comma, negative 3. Okay, looks to me like it's doing this. Oops. Ah! And then on the other side, 2, comma, negative 1/3. 3, comma, negative almost 3/4. I mean, it's doing this. If you plug in 1.5, I believe you get a 1. Let's see. 4 times 1.5 is 6. 6 minus 5 is 1. 2 over 1 is 2. 2 minus 1 is 1. So yeah, it's 1.5 comma 1 if you cared. So yeah, it looks exactly like the parent function. It's just been shifted around. What do you think, guys? Can you identify vertical asymptotes, horizontal asymptotes, and plot a couple points? Can you pull? I'm sorry? What top thing? Can you be more specific? The top curve? Yeah. I connected the dots. What? These are the y values. No, they're not. 2 is right there. 3, 4, 5, 6, they're all above the green line. Yours are above that green dotted line, right? Where is your 2 comma negative 1/3 on your picture? You didn't plot all your dots, did you? Well, there you go. I did. I plotted them all. And I added the point 1.5 comma 1. So what you're going to find when you're graphing rational functions is your asymptotes are going to divide up your xy axis into spaces. So if you think about it, there's 4 big spaces, right? You see that? How my red and green line made 4 big spaces? Rational functions will often, not always, often exist in diagonal spaces from each other. It's not an always, it's a usually, or it's an often. It's just a kind of thing that you get used to seeing. So you might be wondering, like, well, how is it possible that they're next to each other? 1 over x squared. every x value you plug in is going to give you a positive number. So 1 over x squared looks like this, like that. So yeah, it's possible that they're next to each other. You know what's impossible? It's impossible for them to ever be over each other, because then it wouldn't be a function, because it would fail the vertical line test. Right? You can't hit the graph twice with a vertical line. So they can be next to each other, or they could be diagonal from each other. Like that. Does that make sense? Everybody's cool with that? Donald shook his head up and down. Most other people aren't interacting with me. Hopefully it makes sense. Here's what we're going to do. We are going to describe the transformations from the parent reciprocal function 1 over x, which requires us to be in standard form. Then we'll find our asymptotes, and we'll sketch a graph, and we might even find some intercepts. Let's find some intercepts as well, an x-intercept and a y-intercept if possible. And then once it's sketched, we will write down end behavior, which is everything that I need you to do in the homework for questions 1 and 2. I've lost my, here it is. If you look at numbers 1 and 2, it says what's the y-intercept, what's the x-intercept, what's the vertical asymptote, what's the horizontal asymptote, what is it in standard form, describe all the transformations, and get a graph. So question number 1 is 7 things. And I forgot to include on there end behavior. Could have been 8 things. And that's the same thing for number 2. So this is in standard form. Yay, standard form. I see 2 transformations. I see the 2 on top, and I see an x plus 3 on bottom. This 2, is it changing my x's or my y's? The simple answer to that question is, well, is it where the x's are? No, it's not. So since it's not where the x's are, it's forced to be a outside change. Vertical, outside, same. For rational functions in standard form, the inside is where your x's are, so the denominator. So this is a vertical change. It's supposed to be a 1, it's now a 2. Clearly, I multiplied by 2. So multiplying your y values by 2 is what kind of transformation? This is old material, guys, come on. Multiplying your y values by 2, what is it? Yes, this is a vertical stretch of factor 2. The denominator is supposed to be x. It now says x plus 3. What kind of transformation is addition or subtraction? No, it's what kind is it? What kind of transformation is it? It's a shift. Because it's on the x's, is it vertical or horizontal? So I have a horizontal shift, and is it left or right? Left. This is left. Remember, horizontal, inside, opposite of what it looks like. Horizontal, inside, opposite. So it looks like it's plus 3. No, it's minus 3. In fact, for AP Pre-Calc, which some of you are going to next year, we don't even say shift left 3 units. We say horizontal shift negative 3 units. For AP, we don't say up, down, left, right. We say either positive or negative shifting. So we'll say shift left 3 units. Next year in AP, you'll get used to saying it with a negative sign. Shift left 3 units. So if I shift it left, my vertical asymptote also shifts left. So what is now my vertical asymptote? What are you supposed to say? Can't just say negative 3. It's x equals. It's the one number x can't be. It should have been at x equals 0. It's been shifted left, so now it's at x equals negative 3. There was no vertical shifting. That means my horizontal asymptote, which would have come from back here, is still the x-axis. or y equals 0. And you do have to say x equals or y equals. If you don't, it is going to be wrong. Let's find some intercepts, since that's what you have to do for the homework. Let's find which one do you want to find first? X-intercept or y-intercept? I don't care. Somebody say one. The y-intercept. Let's find that first. If we are on the y-axis, what is always true? No matter what, pick a coordinate on the y-axis in your mind. What is true about every single coordinate on the y-axis, Massimo? The x is 0. So if you want to know how to find your y-intercept, you use x equals 0. Oh, I crossed the y-axis at the number 2/3. So x-intercept then. If you're on the x-axis, what is always true? Y would be 0. This is your y value. So if you're saying y is 0, you're saying this fraction equals 0. Someone please tell me, what is the only way a fraction can equal 0? You're not allowed to have the denominator 0. Remember, if the bottom is 0, you have a vertical asymptote. So what's the only way the value of the fraction's equal to 0? If the top is 0, can the top of this fraction equal 0? Nope. What that tells us is this graph has no x-intercept. You know why it doesn't have an x-intercept? Because that's its horizontal asymptote. So it shouldn't be surprising. Let's sketch our graph. Oh, was there any reflecting? No, I didn't multiply by a negative sign anywhere. So look, this is the shape of the parent function, and since I didn't do any reflecting, I'm going to have this same shape. So it's going to look like this on the left and this on the right, because there was no reflecting. Going to draw our xy axis. Picture not drawn to scale. We're going to do our best. We have a vertical asymptote at x equals -3. And we have a horizontal asymptote at the x-axis. And we know we cross the y-axis at +2/3. So if this is 1, I'm going to cross the y-axis here-ish. That means this graph exists here. And then down here. It has to get infinitely close to both of its asymptotes, and we know it had that shape. So it looks something like that. In the homework, how are you going to graph it? You're going to get a couple more points. Just use a calculator, plug a couple more points in. That way you have more accurate pictures than what I just drew. Just plug a couple things in. You don't have to go nuts. Get like 2 points on each side of the vertical asymptote. That'll be good enough. The last thing that we were supposed to do for this one is we need to write down the end behavior. This graph approaches the same y value to the far left and the far right. What y value is that? What y value is it approaching? 0. It's approaching y equals 0 on both sides. So I can actually write it as one statement. The limit as x approaches -infinity of f of x is the same as the limit as x approaches +infinity of f of x, because they both equal 0. So all of that stuff, that's essentially what you're doing in questions 1 and 2. Except questions 1 and 2 are actually more like example B, where I didn't give it to you in standard form. You have to find standard form. And the way we find standard form is long division. The stuff we did in chapter 4. Are there any questions on example A before we move to example B, which requires long division? Everybody's cool. You saw all the skills. You know how to identify the transformations. You know how to identify the vertical and horizontal asymptotes. You know how to find x-intercepts. You know how to find y-intercepts. You know how to sketch. You know how to write in behavior. And you can plug numbers in on a calculator. Okay. Then one more skill, converting to standard form. It requires long division. It won't take much work to convert it to standard form, though. The question is, what do we have to multiply this x by to make it look like a 3x? 3. So put a 3 right there. And we take this 3, if you remember, we distribute it to our x minus 2. It gets me a 3x minus 6. Long division requires us to subtract straight down. Three x minus 3x is 0. That's good. Please remember that when you do minus negative, you're actually adding. So this says negative 7 minus negative 6, which is actually negative 7 plus 6. I have a remainder of negative 1. So the way that you've always seen me write these things then is I've done this. Plus the remainder over the divisor. Correct? All right. Just write this in the opposite order. Can we all agree that this 3 is positive? And are you all comfortable in agreeing with the fact that if there's a negative on the top of a fraction, I could have just said the whole fraction was negative? So like negative 1 divided by 2 is the same as negative 1 divided by 2. Everybody's cool with that? So that is why the standard form of my function is actually negative fraction 1 over x minus 2. And we all said that that 3 was positive. There's standard form. Isn't that neat? So if you write the resulting quotient backwards, you have standard form of the rational function. Pretty cool, huh? Now, can the top of this fraction be equal to 0? Is it a possibility now? Yes. That means this one does have an x-intercept. So you don't look here. You look here. This is just standard form, which describes the transformations, and you can see your asymptotes really clearly, right? But this is where you try to figure out your x and y intercepts because it's easier to do it here. Let's describe our transformations first. Multiplying by a negative, what does that do? It's a reflection. Now, because this is an odd function, well, because the parent reciprocal function is odd, it doesn't matter which way you say are reflecting over the x or over the y. I think it's a much easier thing to just say that that is affecting the numerator only. So let's say it's reflecting over the x-axis. Can we agree to that? Anytime there's a negative sign on the front, do yourself a favor, just say it's reflecting over the x-axis. Because it'll make describing the shift much easier. So we're going to say reflect over x-axis. And it doesn't matter which of the two shifts you say first, so let's just describe our transformations from left to right. What is this going to do? Shift right too? And hopefully the rest of my class knows that. You're not all just going to let Gavin answer. What does this do? Shift up 3. Yep. Okay, let's talk about the shape of this thing and our asymptotes. We reflected it. That means this image is no longer accurate. Since it's been reflected, you have to flip that image upside down. So it's going to do this. That's going to be the shape of this one. And we can use our shifts to figure out our asymptotes. What x value is a big fat no-no? 2. Well, you can't divide by 0, but 2 is what would have made that happen. So x equals 2 is our vertical asymptote. And our horizontal asymptote, remember, is supposed to be the x-axis, which is y equals 0. We said this has been shifted up 3. So now it is no longer the it is no longer the x-axis. It is now y equals 3. We have our vertical asymptote. We have a horizontal asymptote. Let's find our intercepts. Last time, the first one we found was the y-intercept. It's found the same way. The y-intercept is what you get when x equals 0. So look here. If x is 0, what do you get? And here? So what you're actually going to get is negative 7 over negative 2, which is 7 over 2. 3.5. It's easy to graph decimals, easier to graph decimals than it is to graph fractions. So say it's 0, 3.5. Now for your horizontal asymptote though, horizontal asymptote, we already did that. For your x-intercept, we said the only way that the entire fraction could be 0 is if the top equals 0, right? Good thing we've been practicing solving tiny binomials like that for a while, right? Add 7 and divide by 3. 7 over 3, which is 2.3 repeating. We're ready to graph. We'll sketch, I should say. We're ready to sketch. X equals positive 2 is our vertical asymptote. Y equals positive 3 is our horizontal asymptote. We said our y-intercept is at 3.5. And we said our x-intercept is at 2.3 repeating. That tells us that our graph looks like this. Ta-da. The graphs don't need to be pretty. When you're doing your homework, just make sure you hit the x and y intercept and you have the asymptotes correct, and I'm happy. Oh, in behavior, they both approach y equals 3. We're going to do this next question, and we'll call it a day. I hear a couple people starting to rustle papers. Guess they're telling me I need to hurry up, huh? So yeah, all of this, all of that work, that's what you need to do for 1 and 2 in the homework. And the only thing that's different is I gave you grids for 1 and 2. Can you pull that off? You can do that. Awesome. This is numbers 3 and 4. We're going to write the equation of g of x. I've given you the dotted graph of f of x, which is the parent reciprocal function, 1 over x. So this is 1 over x. We're going to use our knowledge of transformations to find the equation for g of x. I would look at the asymptotes first. What x value is my graph not hitting at all? Say it louder, come on. What x value is g of x purposely missing? 3. One person said it. X equals 3 is my vertical asymptote. That means 3 makes the bottom of my equation equal 0. if 3 makes the bottom equal 0, if it's been shifted to the right 3, what does the bottom of my equation say? Transformations, guys. X minus 3. The horizontal asymptote is at what y value? Lots of people, you should all be able to see it. At y equals 1. That means my graph has been shifted up 1. All that's left is for me to figure out what A is. I'm hoping that you're seeing that it's been reflected, so you already know A is negative. But how do we find its value? It's very simple. You find one pretty point that it goes through, and you plug that in as x comma y. Somebody tell me a pretty point that g of x goes through. What's that? 1 comma 2. So it looks like it goes through 1 comma 2. Looks that way. Let's see what happens. Let's plug those in. 2 equals a over 1 minus 3 plus 1. Okay. 2 equals a over negative 2 plus 1. Subtract 1 from both sides. 1 equals a over negative 2. How do we get a by itself? Multiply by negative 2. So a equals negative 2. That means your equation is g of x equals negative 2 over x minus 3 plus 1. Ta-da!